So welcome back, Math Explorers. Today we are setting sail on an intellectual voyage that delves deep into the captivating interplay of weak topology, convex set, and linear operators. So as we navigate this sea of knowledge, intriguing properties will surface from the harmonious fusion of these three concepts. So, but before we dive in, I would like to extend a special invitation to all young mathematicians, especially those from African countries. Please do not hesitate to reach out to me for help or guidance with your studies. So, with that being said, let's start our fascinating journey. So, in our last lecture, we actually our last lecture was actually on the weak topology, and then we saw that every weakly closed set was actually strongly closed, right? And of course, the converse is actually false if you are actually in infinite dimensional spaces. But however, it's actually very useful to know that for convex set, weakly closed, is equivalent to strongly closed. So maybe I write it as a recall. Um, so we saw that every weekly closed set is strongly closed, right? And the converse is false, right? Put it in capital letter in infinite dimensional spaces. So infinite dimensional spaces. So let me highlight that. So if you're actually in infinite dimensional space, so it is not true. So however, it's actually, as I said, useful to know that however, it is very useful to know that for convex set, put it in color. So for convex set, so if your set is convex, then you have equivalence. For convex set, put it down here, weakly close means is equal to strongly close. Okay, so we can state our first theorem, right, and then prove it. So theorem 3.7, and this is actually in continuation with the previous lecture. So theorem 3.7. So let's say be a convex subset of E. Let's say be convex subset of E. Then C is close in the weak topology. Then C is close in the weak topology sigma E star. In the weak topology sigma E star if and only if C is actually strongly closed. If and only if it is closed in the strong topology. The strong topology, I mean the topology induced by the norm. So good. So let's prove that if you have a convex set, then weak closeness is equal to strong closeness. Proof. Okay, and then I think we start with the easier part. So assume it is strongly closed. So assume C is closed in the strong topology. Assume C is closed in the strong topology. And let's prove. So let's prove. Let me put it in. Let's prove. Let's prove that C is weakly closed or is closed in the weak topology. Closed in the weak topology. So basically what we should check is that, so we should check, oops, sorry, it is ugly. So we should check that C complement is actually open. That C complement is open, right, in the weak topology. The weak topology. So let x0, right, say let x0 in C complement, right, that is x0 is not an element of C, right? So since C is convex and singleton x0 is actually is closed, I mean we can actually think of applying the Hahn-Banach theorem, right, to separate x0 and C. So by the Hahn-Banach theorem, so by Hahn-Banach, there exists a closed hyperplane. So there exists a closed hyperplane strictly separating x0 and C. So well, this means there exists a linear bounded operator on E. There is F the joule of E, and there exists a constant alpha in R such that the joule bracket, so maybe write it properly, such that f of x0 strictly less than alpha, which is strictly less than f of y for every y in C. So now put say V being equal to the set of x in E such that f of x is strictly less than alpha, right? So that x0 belongs to V. And V intersected with C is the empty set. So V and C are disjoints. So this means V is a subset of the complement of C. and V is obviously, opening the weak topology. And V is open in the weak topology. Hence, C complement is open. That is open. Let me just for precision. It's open in the weak topology. So this means phi is weakly close. Okay, but so I think that was it, right? So I think the other part is kind of is even easier, right? Because if you assume that that C is actually strongly close, it's actually it's actually really close, then it is obviously strongly close, because we saw that in the last video or in the last chapter on weak topology, that the weak topology is actually closer than the strong topology. So every weakly open or closed set is actually strongly close. So there is basically nothing to do for the other part. So this part is it's trivial. So and then we are done. Okay, so I think finally the hardest part, not really the hardest, but the kind of the harder part was actually to move strong from strong closeness to weak closeness. So okay, so from this we can actually be able to derive an interesting property, corollary to 3.8 here. So this is due to Mazur. So the corollary actually state that, if you have a sequence of weakly, if you have a weakly convergent sequence, then I can always kind of construct, right, a strong convergent sequence out of that weakly convergent sequence. So mathematically, so assume say xn, right, converges weakly to say x, right, then there exists a sequence, right? There is a sequence, say yn, right, made up of convex combination of the xn's, right, that converges strongly to x. Strongly to x. So let me highlight strongly. Okay, good. So basically, if you have a weakly convergent sequence, right, then by convex combination, one can construct a sequence that converges strongly to the same X. So proof. So what? So well, for the proof, we consider the convex role of the element of the sequence xn. So put say C equals the convex role let's call it say P, right? P moving from 1 to infinity. So this is, as I said, this is the convex role of the xn's. So since x belongs to, the weak closure of, so since x belongs to the weak closure of of the union of the x, say P, right? P moving from 1 to infinity, right? This is true because I put it, because you know that xn converges weakly to x, so x belongs to the weak closure of the union of the, of the xpp moving from 1 to infinity. So since x belongs to the weak closure of that set, right, it belongs a fortiori to the weak closure of C. So it belongs, we'll remove the capital letter here, it belongs a fortiori to the weak closure of C. So what I mean is x belong to the weak closure of this. So for this topology, okay, now since C is actually convex, right? Since our set C is convex by assumption, not by assumption, but like by definition, because we define C to be the convex role, so it's actually convex by definition. So since C is actually convex, it follows from theorem 3.7, the first theorem we prove, right? Prove that if the set is convex, then weak closure is equivalent to strong closure. So let me highlight this. So you follow from theorem 3.7 that X is an element of the strong closure of this. X belong to this strong closure of C. So and well, the conclusion follows. So we are done. If X is actually in the strong closure of C, then by definition you can always find the sequence of element of X that actually converges strongly to X, and but element of C are actually convex combination of element of the sequence Xn. So good. So another interesting property is actually related to lower semi-continuity. So Corollary 3.9. So assume you have a function. So assume phi is your function defined from E. So say minus infinity plus infinity included, right? Assume phi is convex and lower semi-continuous. So the LSC, is short for lower semi-continuity. So assume phi is convex and lower semi-continuous in the strong topology, of course, because now you have two notions of topology. So it's actually very important to precise which one we are talking about. So assume phi is a convex and lower semi-continuous in the strong topologies. Then phi is weakly, is lower semi-continuous in the weak topology. People often say, phi is weakly lower semi-continuous in the weak topology. Sigma E star. Okay, proof. Right. So of course we assume that our function is convex and lower semi-continuous in the strong topology, and then you want to show that it is weakly lower semi-continuous. So proof. Maybe before having the proof, let me just recall something very quick. So saying that phi is weakly lower semi-continuous or lower semi-continuous in the weak topology means that if you have a sequence xn that converges weakly to say x, right, then this implies that phi of x, right, is actually less or equal than the lim inf of phi of xn. So this is basically what we are going to show in the proof. Okay, so let me shift this up a bit. Good. So again, the proof is a bit constructive. So for every lambda in R, right, we the set, say capital A, defined to be, this is the set of x in E, capital E of course, such that phi of x is less or equal than lambda, right? So this set is convex, right? Because phi is convex, so and strongly continuous. So for every lambda in R, the set A is convex and strongly closed. Strongly closed, right? Because you can basically see that the set A can be written as the pre-image of minus infinity, this. So this set is actually convex and strongly closed. So by theorem 3.7, it is actually weakly closed, right? Because we saw that for convex set, strong closeness is equivalent to weak closeness. So we close the bracket here. So by theorem 3.7, so by theorem 3.7, it is really close. And thus, I mean, it's enough for us to conclude that phi is weakly lower semi-continuous. And we are done. Well, if you feel like it was a bit too fast, right? So, well, observe that, I mean, if you have a sequence xn that converges weakly to, say, x, right? Then xn is an element of A. I mean, for every n xn is in A, right? It's enough for you to take lambda, to consider lambda to be, say, the lim-inf of, let me drag it a bit, but the lim-inf of phi of xn, right? So this really implies that, I mean, x is in A, right? Because, I mean, we saw that A is actually strongly closed, right? So, and strongly closed, I mean, for a convex set means weakly closed. So, x is in A. So, that means phi of x is less or equal than the lim-inf of phi of xn. So, this is just another notation of lim-inf, right? So, some of you are familiar with that. So, anyway. Okay, so now let's have a remark. Wait, so think so remark. Let's fix something quickly. Good. So the above corollary is actually is mostly or often used in the following form. So the above corollary is often used as to have phi convex and strongly closed. You can even replace lower semi-continuity by strong continuity. So phi convex plus strong closeness plus strong continuity, plus strongly continuous implies that phi is weakly lower semi-continuous. So lower semi-continuity, the strong topology can be replaced by strong continuity. So as an example, we can consider the function phi of x to be the norm of x, right? So phi is convex, obviously, right? By definition of the norm, right? Convex and also strongly continuous. Thus, it is thus it is distributively lower semi-continuous. So in particular, if you have a sequence xn that converges strictly to x, then the norm of x is less or equal than the lim inf of the norm of xn plus infinity. Okay, now we state also a very important theorem about continuity, how strong continuity is actually related to weak continuity. So theorem 3.10. Okay, so let E and F be Banach spaces. Let E and F be Banach spaces. And let T be a linear operator. Linearity is important here. The linear operator from E into F. So let me just highlight linear very quickly. From E into F, right? So now assume T is continuous in the strong topology. In the strong topology. Then T is continuous from A window with the weak topology sigma E star, right, into F window with the weak topology sigma F star, and conversely. So that means we even have an equivalence here. Okay, good. So if you have two Banach spaces, right, and then you have a linear operator, if the linear operator is actually continuous in the strong topology, right, then it's actually continuous for the weak topology, and conversely. So let's have a look at the proof. Okay, so we first assume that that T is actually continuous for the strong topology, right? So and then you want to show that it is continuous for the weak topology. So in view of proposition 3.2, let me shift it slightly. Good. Proposition 3.2, right? So I think proposition 3.2 was actually on the chapter on the courses topology that I strongly invite you to watch, right? the video on the courses topology. It was a very interesting topic. So I think I will put the link at the upper right corner of the screen. So in view of proposition 3.2, I mean, maybe I recall what proposition 2.2 was, was saying. So proposition 3.2 was about, you should have, so say Z is a topological space, right? And then you have a map psi, right, defined from Z into X, and go with the courses topology that we denoted calligraphic G, right? So you saw that psi is continuous if and only if, right, phi I composed with psi, right, is continuous from Z into yi. I think so, right? For every I in I, yeah. Where phi I was actually, our collection of maps, right, defined from X into yi, right? Yeah. So in view of this proposition, right? So in view of this proposition, it is enough. You can identify Z with E. You identify Z with the set E, right? And go with the Wick topology, sigma E star, right? And then the X here, you can identify it with F, and the YI can be identified with R. So so in view of proposition 3.2, it is enough to check that. It's enough to check that for every linear bounded operator F in F star, whether because our X is F here, so the map this is the dual pairing of F and Tx, right? So this map is continuous from E and O with the Wick topology into R. Okay, so but I think the result is rather straightforward, right? But this map right, is actually it's a continuous linear functional on E. This map is a continuous linear functional on E, right? So therefore, it is also continuous in the Wick topology. In the Wick topology, sigma E star, right? Because we saw that open set for the Wick topology are open set for the for the strong topology. So if you have a function that is continuous for the strong topology, it is obviously continuous for the weak topology. And this is actually the case for us here because f is actually a linear bounded operator on f, and t is also a linear bounded operator by assumption, right? Remember what you want to show. I mean, we assume that t is continuous in the strong topology, so and then you want to show that it's continuous for the weak topology. So this was actually the first sense. But in our theorem, we even said that the converse is actually true. So let's assume that t is actually continuous for the weak topology. So conversely, assume t is continuous from E endo with the weak topology sigma E star, right, into F endo with the weak topology sigma F star, right? So our goal is actually to show that T is continuous for I mean the strong topology. I mean when E and F are actually endo with with the topology induced by the norm. So since so we assume that T is continuous from E endo with the weak topology into F. Then because T is actually continuous, then the graph of T, right, is closed in the Cartesian product E cross F, right, equipped of course with the product with the product topology sigma E star cross sigma F star, which is the same, I mean you can prove it, right, which is the same as the weak topology sigma E cross F joule of star. So it follows that the graph of T is strongly closed, right? Because remember, let me put it in color. So remember that always remember that any weakly closed set, any weakly closed or open set, right, is strongly closed. So you should always keep that in mind, right? That the weak topology is coarser than the strong topology. Strongly closed. Okay, so because the graph of T is strongly closed, right, we conclude with the help of the closed graph theorem that T is actually strongly closed because T is linear. That's why I said at the beginning that linearity is very important. So we conclude with the help of of the closed graph theorem. I also did a video on that. A lecture. You have a full lecture on the closed graph theorem and the open mapping theorem. So I also invite you to have a look at that. So we conclude with the help of the closed graph theorem that T is strongly closed. Sorry, that T is strongly continuous. Good. So we are done with the proof, and I think we will stop here, right, for this lecture. And in the next lecture, we are going to talk a bit about the weak star topology. So thank you once again, and see you in the next video.